Hello everybody! Today we're going to talk about the polarization of light. And here's a little demonstration. So when light is polarized, basically that means that all of the light that gets to a location is all oscillating the same direction. Meaning it's all up and down, or it's all horizontal, or all diagonal. It doesn't matter. All the light waves that get to you that are being observed are in the same direction. So here's what that means. Imagine we had light that's not polarized. You have light waves going all these different directions. You have light waves that are going vertical, light waves going horizontal, light waves going diagonal this way. You can have light waves in between there, oscillating in different directions. And what a polarizer does, here's an example of one, it's basically like a filter. It's not technically a filter, but it blocks light from getting through it, but only light that doesn't fit through that opening. So basically a filter like this, a polarizer, has these vertical lines in it, really small vertical lines. And because there's these vertical lines, it's almost like these openings for the light to get through. That means that any light that's not going vertically can't go through it. It's like, you shall not pass, Gandalf. All right, so what that means is that this line, let's say any light that's going like this, can pass through this filter because it has these openings it can pass through. But light going horizontally, boom, 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 when it gets to this filter, it gets blocked. It's like it hits these walls and it can't pass through the filter. So, kind of interesting is that all of the horizontal light gets blocked, all of the vertical light gets through, and then as far as the other light waves that are diagonally, what we can do is think about those light waves as vectors, meaning that, for example, this light wave right here, that's going oscillating like this, like that, we can break it down into vectors. Break it down. Some of that light is oscillating horizontally with this amount of intensity, and some of that light is oscillating vertical with this amount of intensity. Now, if you notice, this line is shorter than this line, but that still means that even though the light is oscillating diagonally, some of that diagonal light can pass through. It's almost like it kind of gets blocked partially, but not all of it. Some of it actually can pass through. And here's what we get. I'm going to look at each one of these lines. Now, in reality, there's going to be like an infinite number of these light wave lines, or just a really high number. I only drew 1, 2, 3 lines. Let's look at those lines and see what lines can actually pass through this filter. So, can this vertical line pass through? Yes, indeed it can. In fact, the entire light wave can pass through. So I can draw that. Hey, that much light is getting through. Muy bien. Can this horizontal line get through? No, it cannot. The line cannot get through, so none of it gets through. Now let's look at this line. It's the same length, but it's diagonal. Now this can be broken down into horizontal pieces and vertical pieces. Now the vertical piece here can get through. This does not. So this part, I'll draw it over here, that can pass through. Same argument with this diagonal line. We have light that's going through this direction. It's oscillating up and down and horizontally at the same time. This gets blocked, but that does not. And we can draw that over here. So here's what we have. We started with this much light initially. It goes through this filter, and we end up with this much light. And it turns out, if you were to add the lengths of all 3 of these arrows up, add the total length of those arrows, and compare it to the total length of these 3 arrows, the length of these arrows is half as long. The total length of all 3 arrows ends up being half as long as those 3 arrows. What that means is that if you start with like 100 watts of light on this end, or 100 watts per square meter for intensity, when it passes through this filter, you get 50 watts of light that pass through. 50 watts of light pass through. So 50% of the light that goes through a polarizer gets through. Let's see if that's true. Here's a polarizer. I have a flashlight here. Boom, there's a flashlight. I'm going to put a polarizer in front of it. And indeed, we do notice it gets dimmer. Ooh, all right, it gets dimmer by about half. It's not fully dim, but it does dim down quite a bit. Now, what happens if we put a second polarizer after it? So now, what if we take a second polarizer and put it directly after this light? So now that the light that gets through this first polarizer is here, we put a second polarizer right after it. And now that second polarizer may be oriented vertical. If it's oriented vertically, then all this light just gets through and you get 50 watts again. But let's say we don't put it vertically. Let's put it horizontally. So now we have a polarizer over here, and all the lines are facing this way. So we rotated this polarizer 90 degrees, or pi over 2 radians, for those of you that like radians. We rotated it by 90 degrees, and we get this. Or we rotated a second polarizer by that much. Well, now, if you look at this light, it has to get through this. And it can't, because all of this light is vertical. It can't pass through this polarizer because this only lets horizontal light through. So with this, the light that gets through is nothing. There's no light that gets through, so it's 0 watts. You got nothing. You got nothing. Nada, not a zinc. Boom. Oh, that's kind of interesting. So that means if we, let's do a little chart here. If you rotate the second polarizer 90 degrees, we get no light, 0 watts of light to get through. Contrary to that, if we don't rotate at all, 0 degrees, if I kept this vertical, boom, 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 then each one of these three can pass through this filter. It doesn't block anything as long as it's perfectly lined up with this one. No angle rotation, then all three of these waves will get through, and we end up with 50 watts. All get through if there's no separation of degrees between the two polarizers. But we can have different angles in there too. Let's go with 180 degrees. 180 degrees would be like, all right, if I take this, rotate it completely around, get 180 degrees, well, now the lines are vertical again. Because if I just rotate this 100 degrees, it's still vertical. Which means that 180 degrees is the same as 0 degrees, so you still get 50 watts. Hey, all right. What about the angles in between there, though? What if I rotate this one at, well, let's go 45 degrees. What if I take this polarizer, rotate it 45 degrees? So about right there. How much of that light gets through? Well, we could do exactly the same thing with these 3 lines that we did with the first 6 lines. Okay? So, I'm going to draw these 3 lines as is. Shaboom, shabow, shabang. And now I have to draw these, like it has to pass through those filters, these openings. So I can think about this long line here as, yes, it is oscillating this way, but part of that line is oscillating this direction. Part of that line is oscillating this direction. You can think about, hey, what if I just tilt my head and look at it this way? I look at the polarizer this way. Now these lines are vertical, and my arrow is just tilted. My arrow's tilted. So basically, yeah, if I rotate it this way, now my arrow is just tilted, and part of it's going vertical, and part of it's going horizontal. And the part that passes through is the part that's oscillating this way. So this gets through for that light ray. So that's what gets through for that. I could do the same argument for these two. The only difference is that they're shorter, so these are going to be a little shorter. So it does indeed get shorter. So in other words, I'll redraw these over here. Now the light is oscillating this way, but these arrows are definitely smaller than that. And if you were to measure the light that gets through on this second polarizer, here's what happens. You get that it's not 50 watts that gets through, it's not 0 watts, but it's actually because we're rotating right in the middle, you end up getting 25 watts get through. So 25 watts, half of that gets through. So you start with 100, then it went through a polarizer, it blocked out half the light. Then you take a second polarizer and rotate just half of a turn, like not a full 90 degrees, but half of that. So that means that half of that light gets through. It's like vectors. And then, well, how do we deal with the other angles? So to deal with the other angles in between there, we can actually come up with an equation. So we're going to use this equation to calculate any angle. What if it's like 31 degrees or 17.3 degrees? What percent of the light will get through at that angle? All right, so let's do that. I'm going to erase this. Woo! So I just want to show you, again, I have two polarizers here, what that looks like. So if I just take a light bulb, shine at you, it's pretty bright. This blocks out half the light right off the bat. Boom! Now I take a second polarizer, and I'm going to rotate the two polarizers with respect to one another. So right now, you have some light that's getting through. As I rotate this outer polarizer here, let's see what happens. All right, it's getting dimmer, and then it goes to 0. There's no light, so they must be at 90 degrees to each other right now. And I rotate it a little bit more, it starts getting brighter again, and then it gets really bright, just like there was only one polarizer here. Now, all right, about there, and then now it's going to start to get dimmer again, real gradual, and boom, no light again. So it seems like it's going through a pattern, almost like a wave pattern. Let's sketch it out. Let's make a little graph here, and let's label these axes. On the x-axis here, let's label that angle. What angle is in between those two polarizers? What's the angle between those two polarizers? And let's get some just relative data, like points here. So we can do 0 degrees. There's no rotation between the two polarizers. They're both vertical. Both the polarizer A is vertical, polarizer B is vertical. They're both verticals. There's no angle rotation. We can do 45 degrees, which means one of them is like this, and the other one's like this, 45-degree angle between them. We could do 90 degrees, where one of them's like this, and the other one's like this, so they're completely perpendicular to each other. We could do 135, just going up by another 45. And we could do 180. And I think that's pretty good. That's good enough. We can keep going. We can do a full 360 if we want to. Whee, like that. But we'll just stop at 180. Good. All right. So now on the y-axis here, let's just write down like how many watts of light that we get through. So like wattage of light. Now we can start with any value that we want to. But I just want to get some numbers based on the numbers I just came up with. So if there was no rotation, let's say gravity dropped that, right? Let's say that 100 watts of light, we start with 100 watts of light. And we had 100 watts of light get through both polarizers at 0 degrees. Let's just start with that. Nice, easy number to remember. If you remember, if I rotated at 90 degrees, no light got through. So we ended up with no light, there's a point there, that got through. If I rotated the polarizers 180 degrees, now both of them are lined up again, so 100 watts of light got through again. 100 watts of light. Now, if you remember, in the middle, at 45 degrees, half of the light got through, so 50 watts. So 50 watts of light got through at 45, and you're going to start to see a pattern here that obviously if you go another 45 degrees past that, you're going to get 50 watts to go through. So we have a couple dots here, and the graph that it makes when you make these dots, you can start to fill in some of these other dots here. It ends up looking like this. A little curvy here, a little wavy going on. Speaking of light waves, you got a little wave pattern here. Woo! All right, so with this, let's write an equation for this graph. Now, if you think about the equation for the graph, it starts at a peak and it goes down and up. It starts at a peak, it goes down, up, down. We can keep going down, up, down, up, down. The equation for that graph is y equals cosine of x times some amplitude, times some starting amplitude. Now we started with 100 watts. So I'll write down, in this graph, it's 100 cosine of x, and the x being the angle. So in this case, this. And I guess, what is Y measuring? I guess Y is measuring like the wattage of light that gets through. So I'll do watt. So the watt equals 100 times cosine of x. Now, we're going to get this more detailed here, like more specific, because this is technically not the equation we want. We want more detailed equation. Now, actually, this is not cosine of x. It looks like cosine of x. It really does. But if you were to take cosine of 45 degrees, for example, if you take cosine of 45, you get 0.707, or about 70%. So that means that 45 degrees should be 70 watts, not 50. So this is not cosine of x graph. It looks like cosine of x graph, but it's actually cosine of x squared. Because if I take 0.707 and I multiply by 0.707, I get 0.5, which is 50%. So this graph is actually cosine of angle squared. So it looks like cosine of x, but it's actually cosine of x squared, which gives you the same shape, but just steeper, a little more intense. And speaking of intense, that's exactly what this graph is measuring. It's not measuring 100, because that was just arbitrary. This would be your initial intensity, I0, or beginning intensity. What intensity of light do you start with? That actually gets through the first polarizer. What intensity of light gets through the first polarizer? And then this is measuring not the wattage, because I just randomly picked wattage, but it works this way. If we're using intensity, let's keep it consistent. This is measuring the intensity of light that gets through the second polarizer. So what does that mean? Well, that means that if I can plug in any intensity of light I want for I0, let's say 100 watts, and I multiply by the cosine of any angle I wanted to, and I square that number, I can figure out how much light gets through the second polarizer. This is called Malus's law. And it's all about polarization of light. Now, polarizers are pretty cool because there's a lot of things that are applied to polarizers. In fact, polarized sunglasses, what they do is you look at the sun, which I don't recommend doing, but it can block sunlight. So if you're out on the lake or something and you wear these sunglasses, it actually blocks 50% of the light that gets to your eyes. It's all oriented in the same direction. You can actually take two polarizing sunglasses and rotate them and actually get dimmer or brighter. Welding helmets, where you get this bright flash of light, it can actually block the light based on using polarizers. Your calculator. When you use your calculator and I turn it on, is this light here? I mean, it's just projecting light through a screen. But then you see, like, if I type in numbers here, blah, 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 88888, what that's doing, how does that show up? All it's doing is it's using a polarizer, and that button just rotates the little liquid crystal polarizer. So it's just a little crystal polarizer, and it's just rotating it to 90 degrees, and it blocks out all the light. So what you're seeing with these numbers here is not black light, you're seeing blocked light, because everything else around it is getting through, and the light can't pass through those little polarizers there. So those are just a few applications of polarizers. So some people really like them, some people don't. They're pretty polarizing. That was bad. All right, so I'm sorry. I will end at that point. I'm going to end the video right there because hopefully you guys are enlightened with this. But other than that, hopefully polarizers make a little bit more sense now.